How does a generator converts mechanical energy into electricity? How can transformers convert 110 volts into 220 volts? How metal detectors detects metals? These are some of the questions that science and technology sought to unravel amidst the mysteries of our ever-changing planet. And for this day, we will be discussing the concept about electromagnetic induction. History of electromagnetism. In the early 1800s, the only current-producing devices were voltaic cells, which produced small currents by dissolving metals in acids. These were the forerunners of the present-day batteries. In 1820, Ørsted found that magnetism was produced by current carrying wires. The question arose as to whether electricity could be produced from magnetism. The answer was provided in 1831 by two physicists, Michael Faraday in England and Joseph Henley in the United States, each working independently and without knowledge of the other. On that same year, Michael Faraday announced the results of his experiments, that current can be induced in a coil. Recall that the magnetic field around a current-carrying conductor is dependent on the current in the conductor. A changing current produces a changing magnetic field. This was the basis of Michael Faraday's explanation of his discovery. With the experimental verifications and satisfactory explanations of his results, Faraday was given credit for the discovery. This discovery marked the beginning of the age of electricity. To have a better understanding about the concept of electromagnetism, we will do a series of activities. The materials needed in the activity are the following. Magnets, solenoids with different number of turns, alligator clips, and a galvanometer. Procedure: connecting the circuit. Connect the two ends of the alligator clips to the ports of the galvanometer and the remaining to the solenoid. We now have the setup for our activity. Using the solenoid with the lesser number of turns, thrust the north pole of a bar magnet into the solenoid. Observe what will happen to the needle of the galvanometer. The needle was deflected. Repeat the previous step, but this time, thrust the bar magnet inside the solenoid faster. Observe the needle of the galvanometer. Compare the degree of deflection with your previous activity. The needle was deflected, but this time, the magnitude of deflection is greater, suggesting a stronger induced voltage. We have just learned that voltage is induced in a circuit whenever a magnet is placed inside a solenoid. In simpler terms, voltage is induced whenever a magnetic field near a conductor changes. Second activity, increasing the number of turns of the solenoid. Using the same setup, repeat the steps that you have done in your previous activity, but this time, try a larger solenoid. What happened to the needle of the galvanometer? Compare the results with your previous activities. The needle of the galvanometer was deflected. The deflection was also stronger compared to the smaller solenoid. In this part, we have just learned that the voltage induced in a circuit becomes stronger when a larger solenoid is used. Simply put, the greater the number of turns of the solenoid, the stronger the voltage is. Third activity, varying the relative motion of the magnet. Utilizing the same setup, perform the previous steps in the procedure, but this time, thrust the bar magnet inside the solenoid faster. Observe the deflection of the needle this time. Compare it with the previous activities. The magnitude of deflection is greater, suggesting a stronger induced voltage in the circuit. Fourth activity, altering the magnetic field. Using the previous setup, perform the last step, but this time, instead of thrusting the bar magnet up and down, alter the position of the solenoid. Observe what had happened to the needle of the galvanometer. The activity suggests that the amount of voltage induced depends on how fast the magnetic field lines are entering or leaving the solenoid. To sum it up, we've just learned that moving the magnet in and out of the solenoid produces voltage. The induced voltage can be strengthened through the following methods. Using a larger magnet. Increase the number of turns of the solenoid. Increasing the relative velocity of the magnet. Here are some of the practical applications of electromagnetic induction. Generators. A generator is simply a stationary magnet with a rotating coil. When the coil inside the generator is moved in and out of the magnet, voltage will be induced. Another practical application of electromagnetic induction is the transformer. A simple diagram of a transformer. Note that one coil of a transformer is connected to a battery or a power supply, and the other is connected to a galvanometer. Usually, the coil that is connected to the power supply is called the primary, and the other is called the secondary. As soon as the switch is closed in the primary and current passes through its coil, a current occurs in the secondary, even though there is no material connection between. A magnetic field builds up when the current begins to flow through the coil. This means that the magnetic field is growing around the primary, but since the coils are near each other, this changing field extends into the secondary coil, thereby inducing a voltage in the secondary coil. An electric motor. The construction of a motor is in principle identical to that of a generator. Only the roles of input and output are reversed. In a motor, electric energy is the input and mechanical energy is the output. In a generator, mechanical energy is the input and electrical energy is the output. Both devices simply transforms energy from one form to another.